Good evening, everyone. This is Marcus. I want to be the project. So our project is basically the title of it is explaining about it learning a bit more like various things and for care is a little bit new west. So I want to be taking this kind of introduction, the public statement, presentation of problems and the objectives. So basically, take it to the introduction and trying to come up and bring ways to how this problem might machine learning techniques solve the problem of local system. So if you wonder what problem is solving, maybe for example, self-medication, many people, instead students or people who they fall sick. For the example of saying, whenever students get fall sick, they carry on the course of medication using drugs like Lydia for pregnancy and paracetamol for headaches and fever. So for this, they end up with their bodies which are time and they are resistant to the drug. So we're finding a way how best to solve this by studying the features of the cells and so in the introductions of microorganisms for some time now has been as emerged that a particular concerning bacteria and other microbes even develop new mutations to survive the drugs. So this is they can now become resistant to the drug. Like after the body takes time, even if you take paracetamol, the headache does not go out, the fever does not go out. So this is where the bacteria changes at least from us where the drug is supposed to fight it in another way or it mutates to another form to survive. Yeah. During this time, patients are supposed to take spectrum antibiotics that target the gram-positive and the gram-negative bacteria to kill it so that the whatever is paining them to stop. Yeah? So for the problem statement, the boiling process of AMR detection using broad spectrum antibiotics have been explained so people carry out self-medication and at some point there is a point and the drug is now resistant to it and they can no longer get better. So we're trying to carry out study we're trying to study we're trying to study the bacterial cells and how best we are going to to add in the model so and come up with them. So for us, the way we are doing it, we're trying to solve the problem by creating meta learners and also carrying out feature engineering, studying features and how best we can, and also carry out explainability to provide proof to our analysis so it can be used in clinical sector. Then for the computational problem, linearly based on generalization to more mutations, deep limited data predicting different profiles for previous lens mutations. And also the black box nature of the machine learning models whereby many machine learning models function as black boxes providing accurate predictions without revealing the underlying biological mechanisms. So and also the large scale genomic data, the bacteria. So for the large scale genomic data, the bacteria is a very many. Studying one by one and each behaving differently. So for our project, we're going to use the CAD data set. And then for the main objective, we thought about to create a meta learner that uses a long short-term memory binary networks architecture for predicting antimicrobial resistance and the benefit of then also to obtain compact and standardized position extensive bacteria genomes to design later learning models to predict the resistance patterns. This we are going to derive and evaluate meta learning. So basically, we're going to carry the AMR detection using meta learners and also find out the relationship between the amino acid and the AMR using feature engineering. So there, I will get more good technical tips. Thank you so much.
Hello, my name is Bisbana William Gad, and thank you, Carlos, for the introduction. I'm here I will discuss the related works that have been done by different researchers about uh, somehow relating to our topic. Uh, there, there are a number of works that have been put across in this same line, where some design the machine learning based approach to identify the drug classes of antibiotic resistance genes from metagenomic data. We had others who sought the presence of, we have others who conducted a survey on on KEMA methods and applications in bioinformatics. We have also another group that try to give an overview of different techniques necessary to build meta learning systems. Also, others discussed an approach to the problem of meta algorithm selection, which exploits the performance of metadata of algorithms on prior tasks to generate recommendations for a given target. And so many other researchers also did some work in relation to our topic. This is our methodology. First, there is
Busy, and I'm here to continue from where my colleague Carlos has stopped. So before you is a representation of a breakdown of our methodology, and our methodology is broken down into four main parts. The first one is exploratory data analysis, and we are analyzing data that we got from the CAD data set. This will include processing, and the processing, as will be seen, will include undersampling and oversampling of the major and minor data sets. This will be followed by KEMA encoding, and KEMA encoding will also be important in our data pre-processing and analysis. KEMA encoding will also be used to provide possible representations of the sequences to feed into the models. Then training of the amino acid analyzer. This will involve KEMA encoding with a K value of 3, since amino acids are made of basically 3 nucleotides. And lastly will be construction of the main models, which are meta learners that are embedded together with long short-term memory recurrent neural networks and convolutional neural networks in combination with the long short-term memory architectures. Moving on, this graph is a representation of the dataset, one of the datasets which represents bacterial sequences and their occurrences. It's a clear example of undersampling of the minority group, which eventually prompts us to carry out the SMART analysis. This graph here is a representation of the antibiotics to which the sequences render resistance, and these will be useful in matching the determined resistances to specific antibiotics. Last but not least is a representation of KEMA encoding. KEMA encoding is so we get a value K, which in the amino acid analyzer will be 3, and we keep moving around the sequence and collecting 3s next to each other, and it involves overlapping in order to eliminate any chances of leaving out any given sequence. Yeah, and lastly, project design. So our project will be designed as shown here. So it will be in two groups, one of them being an amino acid analyzer. It's a basic Python program that will help us to prove a hypothesis of whether amino acid occurrence is directly linked to antimicrobial drug resistance. And lastly, on our right, the second will be a meta-learning model that will use long short-term memory architecture in combination with recurrent neural networks and convolutional neural networks. Thank you so much. My colleague will carry on from there.
Thank you very much, colleagues, for the presentation, and I'm going to take you through the last part of this presentation. So in our project, as my colleagues have earlier on mentioned, we're using the CAD dataset, which contains the bacterial genomes. But ideally, in a clinical setting where we have bacterial samples and isolates, we would have to prepare the isolates, load them onto the Oxford Nanopore machine, which performs whole genome sequencing, which outputs the whole genome of a bacteria. And after it's acquired, it is sorted and then passed on to the KMR encoding stage, after which it is put into our model for a predictive output. So in this model, we hope to implement explainability, and we're going to make use of 4 explainability techniques. The first one being the use of the SHARP software, in particular SHARP Scano Explain feature, whereby each feature will be assigned an importance value for a specific prediction, and in turn we shall be able to identify which KMR subsequence has the greatest impact on model prediction, and this would typically be high for a KMR subsequence with resistance patterns. Then also we hope to use the LIME tool to explain individual predictions as it breaks down the prediction of each instance into contributions from each feature, highlighting how input values affect the outcome. Then we shall also use the alibi framework, and this alibi framework is based on decision rules which define prediction functions, and in this case will be the logical conditions under which a specific output will be predicted. And then lastly, we shall use the interpret ML framework, which will help to summarize how features contribute to the model's overall behavior across the dataset, and also will help to clearly and deeply visualize SHARP and LIME outputs. So we shall evaluate our 2 models using various metrics. For the Python amino acid analyzer, we shall evaluate its performance through its ability to accurately detect amino acids in bacterial genome sequences, as well as its ability to statistically correlate the amino acids with resistance profiles. And then for the meta-learning model, shall be able to evaluate its performance through its ability to accurately predict mutations and resistances, as well as its ability to adapt to new sequences, both of which would happen during the testing phases. And then lastly, we shall evaluate it through the SHARP scores. Our model API would be published using a TensorFlow serving, which is a flexible high-performance serving system for machine learning models. And this API would typically be acquired, would be interacted with in the clinical settings through the interface that we have designed. And once the whole genome sequence is acquired at the using the Oxford Nanopore machine, it would be input at this stage and then run for a predictive output. In conclusion, the rapid emergence and spread of antimicrobial resistance poses a significant threat to global health rendering existing antibiotics less effective and leading to increased mobility, mortality, and increased healthcare costs. So there is need to devise various means which can help to curb the spread of antimicrobial resistance, and having a meta-learning model would do this quickly and effectively. Thank you very much, and we are ready to take on any questions if there is any.